Back with part two here. We've got our first and only example. There's a bunch of bits and pieces though. AI here is fairly routine, right? This is some notation. Now, we could, if we wanted to, calculate what f at g at x is first, get that new function, and then substitute in -2. Or we could just remember what the definition of the quotient function is and write it like this, right? Okay, well, fine. F at -2 is just, what is f at -2? It's -2 cubed minus -2, which is -8 plus 2, which is -6. So on the top I got -6. And g at -2 is an exponential function, 2 to the exponent -2. Negative exponent means flip. 1 over 2 squared is 1 over 4. So I have -6 over 1/4, which looks terrible. But how do I divide fractions like this? I invert and multiply. So I get -24. So this function at -2 is got a value of -24. Okay, I guess. Whatever. Let's keep going. What's this one say? It says, find x so that fg at x is equal to 0. So the product function is equal to 0. So we want x so that this is true. Well, this is an equation instead of an expression, so hopefully we can manage this. Well, this part here, by definition, is just f at x, g at x equals 0. Right? Well, f at x was this. G at x was 2 to the x, I believe. Did I mess that up? No, that's what g at x is, and that's what f at x is. And notice, now I've got two brackets, and the answer is 0. So it's kind of like I can split this into its pieces, just like way back when we first started talking about polynomial functions, that in factored form, we've got two factors, and the answer is 0. Well, that means I have this is true, or this is true. Right? Now, how do I solve that? Well, this is just a polynomial equation, right? This is, now I'm, ticking back to Unit 1, and how do I solve a polynomial equation? Well, I'm going to factor it. Common factor first. Okay, still working because this can be factored, difference of squares. Yeah, I can hear you sort of saying, oh boy, all that stuff that I need to remember. Yeah, all that stuff you need to remember. I told you, this is a great unit for right before the exam. And then now I've got a factored version of this, and I have my solutions x equals 0, x equals 1, x equals -1. And so those are three solutions. And then what about this? When is 2 to the exponent x equal to 0? Or how do we solve this, right? Well, one way would be to try and write the right-hand side. Now I'm thinking about Unit 4, which we just finished on exponential functions. How do I make this side as a power of 2? This is 2 to the exponent what is equal to 0. Or I could just say, oh, well, let's take the log of both sides. And if you didn't get this right away, log of 0 is undefined. This has got no solutions. And I'm hoping most of you out there in math land were screaming at me. I know that that doesn't have any solutions because I was thinking about the graph. When is this graph equal to 0? It's never equal to 0. That's one of the whole ideas. There's no solution. So therefore, the x's that make the product function 0, the x's that make the product function 0 are just these three. Therefore, the solution set is 0, 1, and -1. Well, what does that tell us about the graph? The product function will have x-intercepts at those spots, right? I don't know how the rest is going to work, but I know that it would have zeros at those spots. Andy, what's next? Oh, this sketch. Okay, well, how am I going to sketch this? Well, first of all, I want to have a look at it, and I have a grid going on here in the next thing. This is part B. So for part B, I want to graph this g at f at x. Well, let's have a look at it. G is 2 to the exponent x. F is x cubed minus x. How am I going to do this? Well, I think what I'll do is I'm going to try to start. Now, did I make the? No, that's right. Okay. I'm going to start by graphing the pieces, right? I'll graph the pieces and then put it together by dividing, because that seemed to work okay for sum and differences. So for G, and notice my scale here. I did this on purpose because all the interesting stuff happens right around 0. 1, 2, 2, 4 is there. Negative 1/2. This is g at x equals 2 to the exponent x. That's the top one. I'm going to do the bottom one in green here. So for f at x, how do I graph that? Well, this is a polynomial function. I already saw that the x-intercepts were -1, 0, and 1. All of them slash roots. Yeah, slash roots, starts and ends. Remember that. This is a degree 3, and leading coefficient's positive, so it starts low, ends high. Yep. Yeah, I know. It's a lot of stuff on this exam. What's a little bit frustrating here is I don't know how far up to go. I know that it starts low and ends high, and I don't know what's happening here. But I'm just going to guess. See, I don't know how high to go, whether it intersects. Something like that. And then we'll have to think about what to do. All right, so this one here is f at x equals x cubed minus x. All right, and then how do we get, and I'm going to do this in black. No, not black. I'm going to do it in red. How do I do this? Well, I take each of the values and I divide. So how is that going to work? Well, notice that dividing by 0, I'm going to get an asymptote here. There's going to be asymptotes all over the place here, because anytime I'm dividing by green, and green is 0, I'm going to have asymptotes. So I've got already 3 asymptotes on this thing, because the bottom is 0 in those 3 places. Okay, dandy. Well, how do we do the rest? Well, I mean, one thing I know that this, if I want to think about these little pieces in here, I have this blue function, which is the top, which is just between 1 and 2, and I'm dividing by a negative. So here I could think about what I'm talking about here is the behavior near the asymptotes, okay? So first of all, let's think about x getting close to 0, but from the right. Well, what do I have? I've got g at f is 2 to the exponent x over x cubed minus x. This is what I'm looking at. Well, what do I have? I've got a positive divided by a teeny little negative, right? I divide by a teeny little negative. I know that it's going to go to infinity, right? That's going to be infinity, but it's going to be negative, right? It's going to be a big negative down here. Similarly, same thing's going to happen for x approaching 1 from the left. I'll say y goes to negative infinity. Same thing, right? I'm going to have a positive divided by a teeny negative. Now, that's what happens there. The problem is I don't know how far up this comes, but that's a problem that we've always had, right? So right in here, I'll do it in purple. I don't know. I don't know this very well, so I'll just put a question mark around that. What about here? When x goes to 1, but from the right, well, I have a positive, and again, I'm doing this in my head, a positive, like it's almost 2, divided by a teeny little positive. Well, what happens to y? Y goes to positive infinity. Positive divided by positive is a positive. This is a huge positive. There. Now what happens over here? Well, this is, and if you try a few values, what happens here quickly is the green sort of overtakes the blue. All right, and I'm gonna come back to this in just a second. All right, I want to go over here and finish this stuff, which I consider the easy stuff first, and I'll come back to this discussion in just a moment. Uh, Over here still, what happens? Well, I'm going to have a positive divided by a teeny positive is going to be a big positive. And same thing over here. I hope you can convince yourself that there's going to be like this piece in here. And again, don't know about this. Don't know. What about, and that was, by the way, there was two more of these calculations that I just did right there in my head. What about here? Well, this is, by the way, the end behavior x going to -1 from the left. I'm going to have a positive. The blue function's always positive, divided by a teeny negative. It's going to be down here. Right? This is a huge negative. That's going to be down there. And notice that this number, small positive divided by a huge negative is going to be, small number, small positive number divided by a huge negative. Well, what happens when I have a huge number on the bottom? This is tending towards 0, and it's going to be negative. It's going to tend towards 0 from the bottom. And in fact, I could think of that as a horizontal asymptote. A teeny little number divided by a huge negative number is going to be almost 0. And along this same line, now back to this spot, I know that it goes this way, but what happens over here? Well, for values along here, we could try some, and this is somewhat interesting. If I go and I try numbers like 2 and 3 and 4, and I'm interested in g, which is 2 to the exponent x, and f, which is x cubed minus x, and then I'm interested in their quotient. What do I got? That's 4. This is 8 minus 2, which is 6, and then I get a fraction. I get a fraction. And this is going to be 2 to the exponent 3, which is 8 over 3 cubed minus 3. 27 minus 3 is 24. And then I'm going to get 8 over 24, even a smaller fraction. And for a little while, it appears this is 4 to the exponent 3, which is 64. That's 60. So I get 16 over 60, which is another fraction. It appears that this will come down like this and be a horizontal asymptote at y equals 0. Now a strange thing happens. ... After a little while. And I think it's maybe 10-ish, maybe, something like that. 2 to the exponent 10 starts getting pretty big. 2 to the exponent 10 is, what is 2 to the exponent 10? 2 to the exponent 10 is, well, where's my calculator? Fire up my calculator. What's 2 to the exponent 10? Should have had it ready. What's wrong with you, Restall? You're making me wait. I can hear you complaining out there, and that's a cool function. Don't know what that was. 2 to the exponent 10. Okay, so 2048. But here I've got 10 to the exponent 3 minus 10. This is 1,000 minus 10. 1,000 minus 10 is 990. Then all of a sudden, I have 2,000 divided by 990. That's about 2. Oh, so maybe it's not 0 anymore. And in fact, as I get bigger, this exponential function ends up being huge. 2 to the exponent 100 is a huge number. 100 cubed? Yeah, pretty big. Pretty big, but that's Well, what is that? There's 100, 100 squared, 100 cubed is a million, subtract 100. It's pretty big, just under a million, right? But this number, 2 to the exponent 100, is huge. 100. Huge, huge, huge. E30 means 10 to the exponent 30, a 1 with 30 zeros. This is huge. And so this number is, 10 to the exponent 30 over a million, which is 10 to the exponent 6. This is going towards positive infinity. So for a while, it looks like it ends up being a horizontal asymptote. Then sometime out here, this starts shooting up like this. And check that on the graphing calculator. Check that on Desmos, that it looks like it goes flat, and then it takes off. And I knew this was going to happen because a funny thing, when we talked about rational functions back in Unit 2, we said that, if the top is dominated by the bottom in degree, so this is x squared or something like that, then I'll have a horizontal asymptote of y equals 0. But if this degree is higher, I'm going to end up having no asymptote. Well, what's funny about this is an exponential function is always dominated by a polynomial function when the x values get large. Okay? So the moral of this not so short story is for g over f, it tends to infinity. As x goes to infinity, this function tends to infinity because the exponential function dominates any polynomial function, in fact, for values of x that are large. And try that out on Desmos. So I'm claiming that even if you go a small little exponential function in a huge polynomial function, or even this tiny little exponential function will still dominate this. As x goes to infinity, y will still go into infinity. And you try that out. Okay, dandy. So that's kind of weird, but what's so important about graphing here? And I know this video is getting long, but I'm almost done. The textbook always is all about this intervals of increase or decrease, intercepts and asymptotes. They want you to state all these things. I figure if you can get the graph, you can at least make an educated estimate about things like when is the function increasing or decreasing, where are the intercepts, where are the asymptotes. So that's why I love the sketch so much. And so when you're doing these, you'll need to do some sketches. For some of this, you'll need the TI-83. For instance, if it asks you to find, what is the minimum, what is the maximum, and again here there is a minimum or a maximum or a minimum in here that we don't know. If it asks you for that, we gotta use technology. We gotta use the calculator, right? Or Desmos, or wait for calculus, which we're not ready to do that. We'll have to use technology, and that's it. Have fun with the technology, and have fun with quotients and products.